I have the unenviable task or challenge of keeping you entertained and away from the drinks at the poster session. I'll try my best. As Kyung-Soo said, this work was led by my advisee, Shahrooz Pouryousef. You'll see him walking around with crutches. He has since been advised not to play soccer the week before an important conference presentation. All right, so this talk is about outsourcing BGP to the cloud. I'll begin with what BGP is or how interdomain routing works today. Right? BGP is the de facto interdomain routing protocol, or the top-level protocol that holds the entire internet, or about 60,000 ASs together today. It is a completely decentralized protocol, no single point of centralization anywhere. And it's an extremely policy-rich or expressive protocol, unlike shortest path routing protocols like Dijkstra or Bellman-Ford. So this interdomain routing problem is significantly more complex than intra-domain or single-domain routing problems. It's been widely studied, and it has long-standing, well-known problems. One of the most important ones being it has really long tail convergence delays. So delays on the order of minutes are not uncommon for BGP, unlike milliseconds or tens or hundreds of milliseconds at best for intra-domain protocols. You have other problems like poor control knobs. For example, its prefix deaggregation is abused for incoming traffic engineering. Operators have a hard time grappling with the complexity of these protocols to make them do what they want to do. So often you have to resort to a tweak and pray kind of an approach. Likewise, for security, part of the reason why BGP has a lot of security problems, even though we have on-paper security solutions for it, is because of its lack of evolvability or ossification. It's really hard to bring about any change to this widespread protocol that's deployed, right? So we think logical centralization of routing control, interdomain routing control, is the answer to many of these problems. So what is logical centralization of control? Well, it is what corresponds to perhaps the most famous three-lettered acronym over the last decade in our trade, or SDN, right? That's what it's doing, logically centralizing control and management. The idea is that a remote controller in the cloud will maintain a global view of the network. This is widely used in the industry for single-domain networks today. Whenever there's an update to this global view, this gets propagated up to the cloud, forwarding behavior is recomputed, and then match action rules are propagated downward. All right? So a lot of research over the last decade and widespread embrace by the industry firmly attests to the success of this approach. Right? The main benefits of this approach are hardware-software decoupling, a global view, control data isolation, basically sliced bread. All right? Our problem is how do we bring this sliced bread technology to interdomain routing, which has largely been untouched by this trend, by the SDN trend. And when I say untouched, I mean interdomain routing as in truly multiple domains, not at the edge for a single domain, and not like some companies use it for interdomain routing across all the domains they control. For example, B4 with Google. What are the challenges? The first of these challenges is confidentiality of proprietary policies. It's not as easy as having an AS submit its policy information over to some cloud, some central place, because that would be a third party. There's no reason. There would be a huge resistance from the operators of these networks to share their proprietary information. So there have been other proposals that have proposed secure multi-party computation-like approaches to address this problem, but that's computationally very intensive, and it's been only shown to work at relatively small scales and by constraining the rich expressiveness of the policy routing protocol that BGP is. There's a chicken and egg problem of how do you get to the routing service itself in order to get your routing service, right? And so we can address this problem. The problem of routing to a data center or a small number of replicated data centers is far easier than the original interdomain routing problem. We have decoupled fate sharing now. Any failure of a route or a link or a router on the way to this cloud, or a component failure in the cloud, now creates a separation between the control plane and the data plane, a problem we didn't have before. This is a problem in intra-domain SDN as well, except it's exacerbated in a policy-controlled environment. And finally, we want to assure operators that the forwarding outcomes that they get back from the cloud will be equivalent to what BGP on the ground today will be computing. Otherwise, you don't know what's happening with the cloud, right? You want this equivalence guarantee to have confidence in it. So I'm going to give you an overview of the CIRCA design. CIRCA is our system for accomplishing this logical centralization of BGP, and then tell you how to address each one of the challenges in achieving this high-level design. The high-level design is pretty straightforward, right? Let's say a root cause happens in some domain. Those are different ASs or domains. And let's say this is recognized first by a router. Let's call this router R. It has some persistent storage. It's going to process one root cause at a time. It's going to recognize this root cause, give it a new sequence number, let's say 23. This two-tuple, a router identifier followed by a sequence number, is a root cause label that's globally unique. It'll send upward or cloudward a ground root cause or a GRC message containing this unique label and other information pertaining to the nature of the root cause. So you can include any kind of router configuration information or policy change information here as well, in addition to node up, node down, link up, link down, link events. When it gets to the cloud, it recomputes global forwarding behavior and dispatches match action-like rules to the routers on the ground. And when there's a match between the root cause, like R21 with R21 here, routers go and install those rules, and they do it in the order of the root causes. Sometimes there's opportunities for concurrently installing some of these forwarding rules when they don't overlap in terms of prefixes. So this high-level protocol, it's fairly straightforward. It's not particularly novel. It resembles other kinds of protocols in intra-domain settings. But there are a few challenges. The first of these is, how do we contain the amount of information that's revealed by these ASs to other ASs, right? It's proprietary information. How do we ensure quick convergence? Why are we doing this? We're doing this because we can reduce these long tail minutes of convergence delays to a second or two. We want this to be fault tolerant, and we want this computational equivalence guarantee to be there despite those faults, and we want to be able to prove this formally. And finally, we want this to be able to interoperate with legacy BGP, in particular incrementally deployable. Otherwise, we're never going to see the light of day on this. So I'll start with limited disclosure. We're not doing secure multi-party computation or any fancy crypto. It's very mundane what we are doing. What we are doing is, for every router on the ground, we have a virtual incarnate or an avatar. That's a virtual router with the exact same information as its avatar on the ground has. So every AS has a presence in the cloud, and this cloud is speaking more or less the same BGP protocol as the ground is speaking. So the amount of information shared via eBGP between border routers up there in the cloud is the same as what is shared or can be inferred on the ground today. So that's called virtual pre-play. The cloud routers are pre-playing this protocol and computing the same routing outcomes. Each AS is enclosed in a virtual LAN that limits the traffic that can be monitored by other entities outside it. In this talk, I'm going to assume the cloud network and physical infrastructure provider is honest and non-curious. The paper discusses how you can use secure computing techniques combined with oblivious memory techniques if needed to extend this to an honest but curious infrastructure provider as well. Okay, so that's for limited disclosure. Like I said, we're not doing anything fancy here. How does this help ensure quick convergence? Well, I have to tell you a little bit about what causes these minutes or one of the reasons why you have these minutes of convergence delay in BGP today. One reason is long timers in BGP. BGP is a complex protocol. It doesn't lend itself to a Dijkstra-like formulation or a Bellman-Ford-like formulation. So it's known to have exponential or worse message complexity in the worst case. So more than 20 years back, Labovitz et al. Showed that in the simple 4-node topology, if the center node becomes unavailable or goes down, then you'll have like 48 stages or 48 rounds of messages before everybody explores all the factorial number of paths and realizes there's no path after all. And this particular configuration, it assumes policies that are not widely prevalent. But since then, people have also shown that in widely but not universally practiced policies that are known as Gao-Rexford conditions, even there you can have exponential message complexity, even with just simple provider-customer-like links like shown in this topology. So operators recommend a value that's commonly set to a default of 30 seconds. Okay? People have spent some time trying to optimize this. But then other people have come up with really remarkably creative gadgets like a Christmas tree, or this is like a shark tooth, or a braid, or like frog eyes and chandeliers and whatnot, to make the case that this exponential message complexity is really dangerous. So there isn't much benefit to be had by reducing MRAIs significantly. So do not fiddle with MRAIs is the operator wisdom. So we said, let's fiddle with MRAIs. Because the cloud is different. Why is the cloud different? The cloud has 2 to 3 orders of magnitude higher control bandwidth. So gigabits per second is commonplace today. Tens, even hundreds of gigabits per second is not uncommon, right? On the ground, you have kilobits per second of bandwidth. It's not the bits per second that's important here, but the control fabric bandwidth that I'm talking about, right? 2 to 3 orders of magnitude lower delay diameter. On the ground, it's hundreds of milliseconds. On the cloud, it's about 1 millisecond. Or you can engineer it to be on the order of roughly 1 millisecond. And you have the luxury of control data isolation that you do not have on the ground today. So because of these, we said we're going to completely do away with MRAI timers altogether, okay? And hope that these bad case conditions don't happen. And we empirically, experimentally evaluate this with realistic topologies. So that's one reason why we expect convergence delays to be much orders of magnitude faster. But I've pulled a fast one over you at this, up to this point. There's another question, a tricky question that we have to answer, which is to detect when the processing of a root cause event has converged in the cloud. So the problem is as follows. I told you, send a root cause up, recompute global forwarding behaviors, send match action rules down. Let's look at it one more level deeper from the perspective of a router up there. A router has to initiate the BGP preplay protocol, the virtual preplay. It has to wait till path exploration converges, and then it has to disseminate its modified fib entries back down to its avatar. This is the important part. How does a router know a router playing this decentralized protocol when the processing of this root cause event has converged? There is no such indicator in BGP today, okay? Because it is truly a completely decentralized protocol. If you throw a centralized monitor, then we have now changed the information leakage model. We've changed a number of things. It's central point of failure, congestion, and so on. So we cannot afford that luxury. All right. So this is a 3-phase algorithm that works as follows, the DCD, or distributed convergence detection algorithm. It says, let's say there's a root router, which is the router that first receives the GRC, or the ground root cause message, from its ground avatar. This starts what's called the exploration, or the first exploration phase. Let's say this message results in it announcing BGP update messages to 3 of its neighbors. It may have more neighbors to which it's not announcing something. So those messages are numbered like shown, all right? And the leftmost of those messages may spawn 2 more messages, and so on and so forth, right? So this exploration, this path exploration is going on. Some of these routers may be identical because exploration can revisit some of the routers, all right? At some point, a message is going to fizzle, which means a router received a BGP update message and it caused no change to its forwarding, so it didn't have anything to announce to its neighbors, or it caused some change to its forwarding and yet its export policy dictated it to not announce anything to its neighbors. At this point, this fizzle will be back-propagated. This starts the second back-propagation phase. And when all of the messages caused by a given message have fizzled, that message will also fizzle. So in this case, 011 just now fizzled. Similarly, when 012 fizzles, all the messages caused by 01 have fizzled, therefore it also fizzles. And so on and so forth. When all of the exploration is completely fizzled, the root GRC message has been completely processed, and this begins the dissemination phase, which is simply retracing those paths to tell all the routers, send all the routers a commit message saying, hey, you can now send your updated fib entries down to your ground avatars. Okay? This is the three-phase protocol. We've formally proven safety and liveness properties. The safety says when this protocol terminates, it has truly finished all the BGP path exploration. This is informal. The formal statements are and the proofs are in the paper. The liveness says that this protocol is guaranteed to terminate if BGP policies are safe. That safe has nothing to do with the safety up there. BGP policy safety means there's no cyclic policy dependencies like dispute wheels and so on, which means BGP on the ground will eventually converge. That's when BGP in the cloud is going to converge. Okay? I'm going to address both of these goals together. I'm going to say what is computational equivalence, what do we provide, and how it works despite faults. The key question of computational equivalence is, can CIRCA ensure to operators that routes computed by the cloud are equivalent to those computed by the ground? Right? I'm going to introduce a property here of the ground protocol called ECC, or eventually consistent convergence. If no root cause events happen for a long time, we want the protocol behavior to converge to reflect the state of the just after the most recent root cause. BGP satisfies this property. Any reasonable ground routing protocol will satisfy this property. What we have shown is this route computation equivalence, that is, cloud-assisted routing should compute the same forwarding outcomes as the ground could have computed. Could, because BGP is a non-deterministic protocol, can have multiple outcomes. What we have shown formally is that if ground protocol satisfies ECC, which any natural ground protocol should, then the cloud will ensure route computation equivalence. And we've shown that this holds despite faults and replication of the CIRCA cloud. All right, legacy interoperability. I'm not going to go into the details of this. We've shown two things. One, this design is coexistent with BGP. If you send a root cause up to the cloud and the ground actually can converge faster than the cloud, then you can pick that outcome and everything will still work correctly. We've also shown that if only a fraction of ASs are upgraded to be CIRCA aware, then you can still get the convergence delay benefits in this system, provided it's only for the events that originate and entirely fizzle within this upgraded CIRCA island. I'm going to show a couple quick results. The first is on convergence delay. I'm going to show this with our Quagga-based prototype of CIRCA. All right? We've actually implemented all of the features that I've shown you here. This is the header format. It's very similar to BGP, but introduces a shim layer with all the root cause information details that we need to make CIRCA work. So here's the convergence delay benefit. Okay? We said we'll disable MRAIs. This shows you the convergence delay on the y-axis as a function of the MRAI timer on the x-axis. And the different lines are for different numbers of ASs taken from realistic internet topologies collected by CADA. The thing to notice about this is that all of the delays are increasing monotonically as MRAIs are increasing. So 0 MRAI is the best, which is what CIRCA uses in the cloud. So that's a second or two of convergence delay, even for about 1,200 ASs with 158 core machines that we used, we can get those delays. More compute provisioning means faster delays. The traditional wisdom is that the delay should look like this. This is based on the assumptions of very slow or high processing delays in routers, which are no longer true. So we don't observe this non-monotonic behavior. When we really artificially constrain our compute to unrealistically low levels, that's when we're able to reproduce this kind of a behavior. I'm going to skip over the DCD overhead and show you incremental deployability benefits. This shows on the y-axis the fraction of events that fizzle entirely within an upgraded island that's upgraded to be CIRCA aware as a function of the percentage of routers that have been upgraded. So there's different ways of upgrading it. If you choose routers randomly to be upgraded, then it's very unlikely that events will entirely originate and fizzle within this island. So for example, in that case, you see even after upgrading 80% of routers, only about 10% of events are fizzling entirely within. But if you upgrade in other sort of more realistic, sensible ways, like upgrade tier 1 ASs, or start with tier 1 ASs and upgrade contiguous islands from them, or upgrade along a chain, or pick the small number of ASs that account for most of the traffic and flux in the internet, then you get results of the kind where upgrading 60% gives you 30% of events. Upgrading 60% of routers means 30% of events will entirely fizzle within this island. That's the fraction of events that will benefit. To conclude, I've presented to you CIRCA, which is an architecture for logically centralizing interdomain route computation. Most importantly, we've shown that it's feasible to do global scale logical centralization while maintaining confidentiality of proprietary policies. We have an order of magnitude faster tail convergence delays. There's no fundamental need for having minutes of convergence delays in this protocol. We've shown that route computation is provably correct. That is, it will be equivalent to what ground today could have computed. And this property is true not just for BGP, but for a very general class of protocols of which BGP is just one example. And finally, we've shown that this design is interoperable in two ways, coexistent. That is, it allows you to choose between ground and cloud, whichever is faster. And even if only a fraction of routers are upgraded, you get a non-trivial amount of incremental deployability benefits. Right? So I'll conclude with that and ready for questions.
So one easy question and one harder one. What about IBGP? That's the easy one.
Yeah. So the paper has an IBGP experiment. This extends to IBGP also. In most of the experiments I showed here, they assume single router ASs, but the paper has both IBGP as well as the interaction between OSPF, like interdomain protocols, with IBGP and eBGP.
And the second is, what if your cloud provider that you're putting these avatars in uses BGP to connect their data centers together?
Sorry, can you repeat the question?
What if the cloud provider you put your avatars in uses BGP to connect their data centers together?
That's a good question. So what I didn't talk about, so the question is about, this is the chicken and egg, this is related to the chicken and egg routing problem, right? How do you get to the data center, and how do those replicated data center locations talk to each other? There's a routing protocol needed to get to your routing, to make the routing service work. Well, the answer to that question is that the problem of routing to one of the data centers from anywhere in the world, one of 3 or 5 replicated data centers, is a lot easier than routing from all 60,000 ASs to all other 60,000 ASs. That's one reason. So the scale of the problem is less. The second is that you do not have to have the richness of policy expressivity for that control plane protocol as you might want for the data plane protocol. So a simpler hop count routing protocol might be acceptable. You may also want policy compliance there or policy expressivity there, and our paper has results on sort of to the extent you want policy expressivity, how do the overheads, availability, despite link failures and so on, compare for those different options. But the bottom line is it's a lot simpler protocol to route to one of a small number of data centers than to the entire world.
Hello, Alexander Azimov, Yandex. I wonder if you're familiar with the principle of hot potato routing.
Yeah, of course.
And do you understand to deliver this kind of service? Because if you are moving something into the cloud, after that you are providing a service. You will also need to send not only a policy about BGP, but the dynamically changing metrics of IGP routing.
Right, exactly. So one of the things that I didn't cover in detail here, but that's described in the paper, is how to express these root cause events. The root cause events could be any kind of information, including any kind of information stored in router configuration files, as well as operator-managed things like local preferences, IGP link weights, and so on. So anything that affects forwarding behavior in the ground is going to be shipped up, and it'll have the same control plane protocol running. So if an IGP weight changes that causes hot potato routing to change interdomain behavior, that'll get propagated up there and be recomputed accordingly.
I will not ask about the computational cost of this, because you are going to have both data derived from numerous networks. But, okay, I will ask another question. You were telling about islands, that there is an opportunity for incremental deployment. And so the networks that will be ready for these upgrade will receive from the cloud the state that should be used before they receive the exact update through the old style BGP. I think that there will be numerous dynamic loops because of these race conditions. Because networks will be expecting, okay, I have a new state, but the new state is not ready. Because intermediate hops haven't changed their control plane, haven't changed their data plane. The packets will be sent to a path that is not ready.
Yeah, it's a good point. So let me try to rephrase the question. The question is, if ground and cloud protocols are simultaneously running, and different routers adopt these outcomes based on whichever one converges quicker, you'll have race conditions. We address why the correctness, the route computation equivalence is preserved despite this, because we have additional mechanisms in the paper to ensure that these race conditions don't disrupt what is the equivalence of what is being computed by the cloud. Those mechanisms I didn't talk about here, but you have root cause event tracking in the ground protocol to prevent those kinds of race conditions.
Okay, we're already over by 10 minutes, so let's take other questions offline.
Well,
Okay. Let's thank our speaker.
Thank
This
you.
is the